The last class we talked about methods of preparing soluble salts, where we talked about other stuff as well. We talked about formation of salts, right? A salt is a product of a neutralization reaction between an acid and a base, right? And it is a compound in which all the hydrogen ions have been replaced by metal ions or by ammonium ions, right? Then talked about salts can be soluble or insoluble. So all sodium, potassium, ammonium salts are soluble. All nitrates are soluble. All chlorides are soluble except for lead and silver. All sulfates are soluble except for barium, calcium, and lead. And all carbonates and hydroxides are insoluble except for sodium, potassium, and ammonium, because these guys are always soluble, right? And so you get that salt from that particular acid. So you get carbonate salts from carbonic acid, sulfate salts from sulfuric acid, chloride salts from hydrochloric acid. Then we talk about oxides. So non-metallic oxides, right, and carbon dioxide, when they dissolve in water, they're acidic. They produce hydrogen ions. Metal oxides are bases. When they are in aqueous solution, they produce the hydroxide ions. Amphoteric oxides, which can act as both acids and alkalis, produce salts. To produce salts such as zinc and aluminum oxide, so those are there as well. Methods for preparing salts, soluble salts, in fact, basically reacting an acid with either an excess of metal, an excess of insoluble carbonate, an excess of insoluble base, or an alkali by titration, right? You're using excess so that all the acid, all the protons that are released by the acid are reacted. So there's a complete reaction. And the alkalis, right? What's the difference between an alkali and a base? An alkali is a soluble base. So if it forms an aqueous solution, the base is then called an alkali and gives up hydroxide ions. So the first thing is an acid with a metal, right? Gives you a salt and hydrogen gas is released. This is used for less reactive metals such as magnesium, aluminum, zinc, iron, and tin. You use, for example, dilute hydrochloric acid, adding an excess of the metal. In this case, we're using magnesium. Effervescence of hydrogen gas will be observed, and you will get magnesium chloride. Here's the equation, the ionic equation, right, and the full equation. And right, how is hydrogen gas being produced? So it's receiving electrons from the magnesium metal to go from the proton to its molecular state. Then once the magnesium chloride is formed, we remove the excess magnesium by filtration. You evaporate the solution and make it saturated. Dip a cold glass rod into the hot solution. If salt crystals form at the end of the glass rod, that means the solution is ready to crystallize. You leave it to cool, forming crystals of magnesium chloride. You filter and dry it with clean tissue papers. And yeah, so you have your salt, right? Now, saying that a salt is soluble does not mean that it is always an aqueous solution. It means that it can dissolve in water, but you can have it in solid powder crystal form as well. Right, now to continue, right, next up is the reaction of an acid with a carbon. And so what you're looking at is acid plus carbonate. Will give you a salt, water, and carbon dioxide. And carbon dioxide, obviously, gas. Right, so you can use this method. You can use a metal carbonate plus any acid, right? And the salt that you will get is a soluble salt, right? The procedure is pretty much the same as we saw with an acid and a metal. And what you will observe in this case are effervescence, the production of a gas, in this case, carbon dioxide. So as an example, you're taking, right, copper 2 carbonate. So copper carbonate, and you're reacting it with nitric acid. And what do you think you'll get? What kind of salt will you get? Any ideas?
Sir, Hannah wants to answer.
She does she?
Yeah.
Yes, Hara.
Yeah,
Any idea what kind of salt you'll get?
uh,
No.
copper carbonate nitrate.
Copper
I guess.
nitrate. Copper nitrate. Good. Good. So you're going to get copper nitrate plus water plus, right, carbon dioxide. Now, how does that look? Right, if you write out the equation, you've got CuCO3, it's a solid, plus HNO3, that's aqueous. It will give you CuNO3 twice, which is also aqueous, it's a soluble salt, plus H2O, which is a liquid, plus CO2, which is a gas. All right, let's balance this thing. What do we do to balance it?
Well, the wait, oxygen is not balanced,
Is it just the oxygen that's not balanced?
and also
Copper.
Copper is balanced. You've got one copper here, you've got one copper here.
the one beside copper is carbon, if I'm not wrong.
Carbonate.
Yeah, carbonate.
Well,
It's
look at carbon. How many carbons do you have here? You've got one carbon over here. You've got one carbon over here. So that's balanced.
yeah, oxygen is not balanced.
You've got 6 oxygens over here. You have 2, 3, and 6. So that's 9. So you have 3 more oxygens over here. What about hydrogen? You've got one hydrogen, you've got 2 hydrogens. You've got one nitrogen, you've got 2 nitrogens. So how can we solve this problem?
We'll put 2
Where?
on the reactant side
Where?
for HN beside HN.
HNO3,
Yeah,
nitric acid.
yeah, we'll put 2 there.
And so now you
It is
have
balanced.
3 and 6. So that's 9 oxygens, which you have on the product side as well. 2 hydrogens, so that's balanced. 2 nitrogens, so that's balanced. All right.
Any more balancing?
Not at the moment. I mean, just getting there.
Okay.
Right. So the metal carbonate contains the carbonate ion, right? And the carbonate ion looks like this: CO3 2 minus. And this reacts, right, with the hydrogen ions in the acid. So we've got an ionic equation over here. You've got carbonate ions plus hydrogen ions that will give you water and carbon dioxide. So you have CO3 2 minus plus H plus, giving you H2O plus CO2. Right? This guy is aqueous. So is this. And then you've got water, that's a liquid, and carbon dioxide, that's a gas. Now, what would you do to balance this? Should be simple, given that we balanced it up here.
Uh, there are 3 oxygens on the reactant side and
3 on the product side, that's balanced. The carbon is also balanced. The only thing that's not balanced is the hydrogen.
so we are gonna add 2 on the reactant side for hydrogen.
And you have a balanced ionic equation. Okay.
Yeah.
Now, in this case, again, right, you will be adding excess of the metal carbonate. And so the unreacted carbonate will settle at the bottom of the beaker or conical flask or whatever you're doing your work. Okay. And then how do you isolate it? It's the same as we had over here. Remove the excess magnesium. So you're removing the excess metal carbonate by filtration. Then you are evaporating the solution to saturate it. So same over here, you're evaporating it to saturate the copper nitrate. Then when it's hot, you're going to dip a glass rod into it. You're going to do the same thing over here. If crystals form at the end of the cold glass rod, right, then you leave it to crystallize, and then you will filter it and dry it with clean tissue papers. Right. So the same thing. Right. So how do you isolate the salt crystals? It's the same as with acid plus metal. So I'm not going to rewrite that whole thing. Any questions?
No.
No. No.
Hmm. Okay, next up is the reaction of an acid with an alkali.
You can mix acid with alkali.
And alkali is just a soluble base,
Okay.
right? So as we mentioned in our review, we did that last time. Alkalis are soluble bases, right? So, right, if you've got insoluble bases, such as we'll talk about oxides and hydroxides, then they're still bases. They still have that whole pH thing and everything, but they just can't dissolve in water. Whereas alkalis are the ones that can dissolve in water.
Okay.
Okay. Now, obviously, all of these are neutralization reactions, right? Uh, in this case, what you're using, right, are alkalis or soluble bases of the highly reactive metals. Which ones? Which are the very reactive metals?
Sodium,
Sodium and
Magnesium.
magnesium,
you use magnesium.
aluminum,
No.
Potassium.
Yes. The two most reactive metals you have, right? And in, like, available and laboratory use and all of that. I mean, they're even more reactive metals, but those are not the ones you normally deal with. So we're not talking about this. Okay. So, right, for these guys, because they're so reactive, like you did with magnesium, you put magnesium ribbon into the acid. You're not going to do that with sodium or potassium. You're not going to take a lump of sodium and toss it, because adding these metals directly to the acid is very dangerous. Right? And so you use the soluble bases, the alkali form of these guys, which are basically sodium hydroxide, right? So NaOH and potassium hydroxide. So KOH. Now keep in mind, most metal oxides and hydroxides are insoluble. Right, we talked about that over here. Yeah. So carbonates and hydroxides. Right, we talked about the hydroxides, we talked about the oxides. Right, we didn't talk about the solubility over here. So, right, most metal oxides and hydroxides are actually insoluble. So the ones that are soluble are called alkalis. So, right, and so you will have, right, these are insoluble bases. The ones that can dissolve, like sodium and potassium, because all sodium, potassium, ammonium salts are soluble, the hydroxides are soluble, right? And so those are called, either you can either call them soluble bases or you can call them alkali, both works. Okay. Uh, so in the book, they've given you a table with examples of soluble bases and some insoluble bases. Right, so the example of soluble bases are obviously sodium, potassium hydroxide. Examples of insoluble bases, for example, are, right, iron oxide. So we know this guy, it's rust. Iron 2 oxide. And then you've got copper 2 oxide, for example, or magnesium oxide, which, right, we formed earlier on. So we can do magnesium oxide, which is MgO. So just an example. Now, what do we do, right? So for this reaction, we use a procedure called titration. And in this, we add the alkali to either a beaker or a conical flask. Sorry, flask. Right? And it's a measured volume. So it's not just, oh, pour it in like you're having a glass of water. So it's a measured volume of an alkali. And then, right, you fill an instrument called a burette with the acid, right? Oh, and you also add an indicator solution to the alkali. Then what you do is that you slowly add acid from the burette to the alkali in the beaker or the conical flask. And what will happen, right, when it reaches what is called the end point, right? Because it's a neutralization reaction, what does the end point mean? Which it means that, right, all the alkali and acid have reacted, right? So neutralization has occurred. And if neutralization has occurred, you're probably going to have a pH of 7 or something, right? So what would happen is that the indicator would change color. What you do is that you note how much, so the volume of acid you used. Now, next time when you repeat the experiment, you take the same measured volume of the alkali, and this time, right, you know how much volume of acid you need to add to neutralize it, because you did it the first time. So this time you can do it without the indicator.
Okay.
Okay.
Yeah.
So that's basically what's happening. Now, as an example, we're going to go back to our very well-known reaction between hydrochloric acid and sodium hydroxide. Right? So again, we can't use sodium metal directly, so we're using an alkali of sodium, which is sodium hydroxide. So, right, you've got hydrochloric acid plus sodium hydroxide will give you sodium chloride and water. So that would look like this. You've got HCl aqueous, NaOH aqueous, giving you NaCl, which is also aqueous, and H2O. What about balancing?
Well, it's pretty much balanced except the uh H HCl.
Hydrogen.
Yeah.
We have to.
You've got two hydrogens. You've got two hydrogens, so that's balanced.
Oh, that's balanced. Okay.
You've got one chloride, you've got one
How?
chloride, one sodium, one oxygen, one oxygen.
Like how hydrogen is balanced?
One hydrogen over here with the HCl,
Yeah,
one hydrogen over here with the OH,
yeah,
two hydrogens over here.
yeah.
Okay? So it is already balanced. So we're good to go. Now, because obviously this is a neutralization reaction, the ionic equation for neutralization reaction, do you remember that?
Yeah.
What is it? Can you tell me?
Yeah, Hiram, can you tell me?
Oh, come on, stop doing that.
I don't know that chapter.
I mean, we did it earlier in this chapter.
Yeah, like I have covered 2 chapters now.
This
Oh,
is.
oh yeah, oh yeah. Okay,
Oh,
okay.
yes, 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 of
I
course.
now I remember.
Uh huh.
Yeah.
Right, so this is the uh, ionic equation for the neutralization reaction. So you've got H plus coming from the acid, which is the hydrogen ion or the proton. You've got
And
the,
OH minus.
that's called the hydroxide ion.
Yeah.
You should learn these names. You should right. So you need to learn
No,
the.
I'm telling the symbol. Yeah, I know.
No, no, I'm just saying.
Yeah.
I'm sure you're studying super hard.
Oh yeah, definitely.
Okay, you need to learn the names. You need to learn the symbols. You need to learn their oxidation states. Right? What's the oxidation state of a carbonate? Oxidation number. What's the oxidation number of a carbonate?
3, I guess.
CO3. What's the oxidation number that comes up here?
Minus
Okay, it's minus how many?
2.
Yes. Okay. So you need to learn the and all the other, like you need to, right, get this into your system. They should, like, flow in you like blood. Right? It should be all through you. And so you're going to H2O, which is a liquid. So that is the ionic equation for the neutralization. And then, isolating it is the same. So procedure to isolate salt, same as previous. So I'm not going into that. It's given in the book again. We've written it down again. I'm not repeating it, right? It's the same thing. Okay, are we good on time? We still have about half an hour. Okay. Next up, so far so good. Any questions?
Yeah.
Questions?
No questions.
No
I'm
questions.
good.
Aram?
No.
Okay. Then you've got an acid reacting with an insoluble base. Right, so this method is used to prepare a salt of an unreactive metal. Such as copper or lead. So the react again, like,
Or gold.
well, the gold is not going to react easily anywhere, right? You do, so you're not going to go into that.
Uh,
Okay. So uh, just a sec, sorry. Just lost my train of thought for a moment. Okay, coming back. So why are we doing this? We're doing this because, right, a reaction of an acid with the metal directly is not possible. In this case, so acid plus metal, not possible. It doesn't work.
Yeah.
Right? It's not the same as what we're saying with sodium. In sodium, it's dangerous to do it. That's why we're not doing it. Over here, it won't work. That's why we're not doing it. So different
Okay.
reasons. And so what we do is, for example, we use a metal oxide and we need to heat it. So we actually need to, provide energy to get the reaction going. So, for example, you are taking, right, sulfuric acid and copper 2 oxide. And you're going to warm it. Right? And so you're going to end up producing which salt? Can you tell me?
Uh,
Can you please repeat it again?
Which part?
Like what you were saying right now.
You are going to react sulfuric acid,
Yeah.
right, with a metal oxide. In this case, you are using copper 2 oxide. And as I mentioned, you need to heat it, right? So you're going to warm, you're going to add these two. Copper 2 oxide is insoluble, right? Sulfuric acid is obviously aqueous. You're going to add the copper 2 oxide crystals to sulfuric acid. You're going to warm this. My question is, what kind of salt will you be getting? Can you guess?
Sulfur oxide.
Well, no.
self. Uh,
It's like
Copper sulfate.
a salt. A salt is basically a metal and a non-metal.
Copper sulfate.
Exactly. So you're going to get copper to sulfate and water. Right. So if I just, I don't know, go back and add it over here as well. Right. Salts are, right, a metal and a non-metal. So written over here as well. Okay. Now what does the equation look like? So you have, for sulfuric acid, you have H2SO4, which is aqueous, plus CuO, which is a solid because it is insoluble, right? And you're going to get CuSO4, copper 2 sulfate, which will be soluble, and you're going to get water.
it's, uh,
It's balanced.
It is balanced.
yeah.
Good. Okay. Right now, metal oxides contain the oxide ion. which is the O2, sorry, O2 minus, not O2 minus, right? And so the ionic equation for this reaction, right? One, you've got the neutralization. What is that? Well, in this case, you don't have an OH, so it's going to be slightly different. So you've got H plus O2 minus, right? This guy is coming in as an aqueous, this guy is coming in solid, and you are getting H2O. Now this needs balancing. What will we do?
Add 2 to the reactant side
Here
for hydrogen.
for hydrogen,
For hydrogen.
right? So this could be one of the ionic equations, right? In this case, because you don't have a hydroxide reacting, it's not an alkali or a base. Well, I mean, it is a base, but it doesn't have an OH, it's an oxide. It's not a hydroxide. And so, right, this is not going to happen. So you just need to be careful about that. I did say that this is the ionic equation for neutralization, but that's only in case where you've got the acid and the hydroxide ion. Here you don't have the hydroxide ion, so this is what the equation will look like. So keep that in mind. Or we can talk about the copper, what's happening to the copper, right? So you've got EuO, which is a solid, and it's reacting with the acid and giving you, right, how will you balance this one?
We are gonna add 2 to the reactant side for hydrogen.
And also copper.
Copper's fine. This is the oxidation number. It is not the number of atoms.
Okay.
Right? The number of atoms comes down below, like the H2. So it's coming out.
Yeah, yeah. Oh, okay.
Okay. So either of these two can be the ionic equation for this particular reaction.
So does okay.
Yeah, go ahead.
No, it's fine. Okay.
Next up, we have reaction of bases with ammonium salts. Right, so this is a procedure that can be used to, make ammonia in the laboratory. What do you do? You take an ammonium salt and you react it with a base. So for example, you've got a base such as calcium hydroxide, right? This guy's insoluble. And you have an ammonium salt such as ammonium chloride. And because it is ammonium, it's going to be soluble because all salts of ammonium salts are soluble. And so this is going to give you calcium chloride plus ammonia and water. Yes, Haram, you have a question.
Like, does every equation has its own ionic equation?
Yes. Right. Now, for example, the neutralization, if you have an OH, if this would have been an OH, it would have been copper hydroxide, for example. then the ionic equation would have looked similar to this, right?
So, sir, isn't this one like the specific for all equations, right?
Well, yes, it depends on what's reacting, what the oxidation numbers are, how they are changing in the reaction.
So this isn't the specific one for ionic equation, right?
The ionic equation, an ionic equation just looks at how the ions are changing,
Okay.
right? For example, over here you've got hydrogen ions, you've got the oxide ion. We're looking at how the ions are reacting to form the compound, in which this case is water,
Yeah.
right? Or how the compound copper oxide is reacting with the hydrogen ions, right? Water is being formed, and then, right, the copper ions are being produced, which will react with the sulfate ions to form copper sulfate. So
So it's the
yeah,
second one.
huh?
So it's the second one, right?
It's the second one, meaning
As in that we are getting the same elements as shown.
this is the overall reaction,
Yeah.
right? I mean, you could write it like this, right? You can write
Yeah.
2H plus, right? SO4 2 minus plus Cu2 plus O2 minus, giving you Cu2 plus SO4 2 minus plus 2H plus O2 minus.
Okay. Okay.
Now, which parts over here you've taken this and this and made this. Over
Yeah.
here, you're taking all of this and the hydrogen, and you're only looking at how the copper is changing, and you're forming water. But you put all of that together, it comes up to be the whole equation that we have up here. So there's nothing different. It's just how you're looking at it.
Okay.
Does that make sense?
Yeah.
Okay. So I think this will be the last thing I'll be talking about today. There are, preparation of insoluble salts and testing for different ions and water of crystallization. So I'll leave that for tomorrow. Perhaps tomorrow's class will be a bit shorter as well. But yeah, so this is the last topic for today.
Okay.
So, right, to write that out, you've got calcium hydroxide, so right, plus ammonium chloride. So this is NH4Cl. This guy is a solid. This guy is aqueous. And what you're getting is calcium chloride plus water plus ammonia gas. Now we need to balance this thing. What are we going to do?
There are two oxygens on the reactant side. No, I'm sorry. It's already balanced.
It is not balanced.
Wait, Cl is not balanced. On the reactant side there is one, and on the product side there is two.
All right, so there's two over here. We're going to add two over here. Now let's see what previous time. You've got one calcium, you've got one calcium. Okay. Right, you've got two oxygens here. You've got one oxygen here. So that's a problem. How many hydrogens do you have now? You've got two
Two.
and 8. So that's 10. And over here you've got, right, 2 and 3. That's 5. Acha, that's a problem. The chloride is balanced, so that's fine. You've got two nitrogens here, right? Only one nitrogen. So I think I'll add two over here,
Yeah.
right? Now with that, hydrogen has changed. So the nitrogens become balanced, but the hydrogen has changed. So how many hydrogens do I have now? I've got 2 and 8, 10 over here, 2 and 6, 8 over here. So it's still not balanced. Now I've got two oxygens here, one oxygen here. I'm putting in a 2 with the water. So now
Which will make four hydrogen.
4 and 6 will make 10. So 10 and 10 will become balanced. Oxygen will also become balanced. And we're good.
Yeah.
Okay.
Yeah.
Now, what basically you're doing, right, is you are heat ammonium salt with base. It will produce ammonia gas, right? This guy will turn damp red litmus paper blue. So it will go from red to blue. Plus, it has a pungent smell, a very unpleasant smell. So in a laboratory, you do not work with ammonia in the open. There's a section of the laboratory called the fume hood, which has an exhaust over it. You only work with ammonia over there because as soon as it's produced, you want to suck it out. You don't want that smell to spread in the laboratory because that will make the environment of the laboratory very unpleasant and you wouldn't want to work. Okay.
Yes.
And yeah, that's all for today. Any questions?
No, sir.
Okay, then I'll see you guys next class then, inshallah.
Inshallah. Allah Hafiz.
Allah.
Allah.